Hi, how's it going? I'm Malachi, CEO and engineer of Elite Automation. So today I want to go over one of the fundamentals of robotics, servos, vision location, line tracking, and different technologies like that. One thing that all these systems have in common is they all work off of what is called Cartesian space or a virtual world coordinate system. And the reason why I say a virtual world coordinate system is because it's technically not part of our true world. And that is where this true fundamental lies, is that all of these systems need to have a relationship from our physical world, so our 1 inch, to a virtual world's 1 inch. And whenever it comes to a piece of software or a servo drive or vision, it doesn't know what 1 inch equals. So on our end as the programmer and controls engineer, we have to set up what that 1 inch looks like in the virtual world. If you're not familiar with the purpose of what Cartesian space is and how it's utilized, essentially it is where you teach your points, where your pickup locations are, where your place locations are. If you're commanded to drive to run a certain direction and then stop, all these systems are taught in a coordinate type of system. So all of these points have a coordinate point to them. So whenever you're programming your robot or your servo, you're writing in there particular positions for it to go to, and those particular positions are assigned to that coordinate system. And when it comes to robotics, you're almost always going to be working in what's called a 3D coordinate system. So you're going to have an X, you're going to have a Y, and you're going to have a Z. Majority of the time, your Z is going to be your up and your down, and then your X and Y will be dependent on your particular application, and different individuals like to do things differently. Sometimes people like to have X positive and minus going with the line. Sometimes it's some other feature in the cell they want it based off of. But majority of the time, you get to choose what is your X positive, your X negative, your Y positive, your Y negative, your Z positive, your Z negative. You essentially get to choose those. Well, you at least get to choose two of them. The other one just kind of flips. If you have your coordinate system like this, by the way, this is called the right-hand rule. This will help you map out your coordinate system and always keep it lined up appropriately. So your pointer finger is your X positive, your middle finger is going to be your Y positive, and then your thumb is going to be your Z positive. And so if you want your X positive to be in this direction and you want your Y positive to be in that direction, then you don't need to change anything. But let's say, for instance, you want your Y positive to be in the other direction. What happens is it flips. So now your Z positive is down, and then your Z negative is up. And let's go back to here. And then same thing with the inverse of that. If you want to change your Z positive to be Z negative, then it flips it again. And then you can even have the option where I believe in like SolidWorks and whatnot, your Z is actually like sideways or something like that. So in that case, it's going to flip it like this. So now your Y is technically your up and your down. Almost always when it comes to robotics though, you're going to have your Z be your up and down, and then your X and Y can kind of be defined by you in your coordinate system. All right, so now let's go ahead and go into some of the methods of how you tie that to this real world. And this is going to really help you understand like the relationship of how this virtual world gets intertwined and matches up to the real world. And generally how that works is you go through either some type of calibration or scaling, and through that calibration and that scaling you create a 0 point. So what is calibration and scaling? So calibration is more so going to be utilized on a device that has the ability to detect a position. So let's say, for instance, if you have like a known position, let's say for instance a limit switch on this end and a limit switch on this end, and you're able to run a servo down here and run a servo down there and touch both ends, and then you have in your software it's predefined, or it's predefined in whoever the vendor is software, that is 10 feet exactly. So if you know that's 10 feet exactly, then you can have your servo system or whatever it is that you're working with kind of auto-calibrate itself. So you don't have to do a lot of the math. The math can be handled in the background. That's either somebody has to program in that math, or the math is already programmed in by the vendor that you got the product from. So what occurs whenever you're doing your auto-calibration, your servo is driving down to one end, touching the limit switch, driving down to the other end, touching the limit switch, and your servo is going to have an encoder on it, or you're going to have it somewhere in that gearing system, in that mechanical gearing system. That encoder is sending that data back to your servo. Your servo has an encoder on it, and so what's happening as that servo is tracking back and forth, that encoder is ticking and sending what's called pulse counts majority of the time to the servo drive. You have some that are like Ethernet based and it's directly doing the pulse counts within the encoder, and then it's just sending like an Ethernet, like IO link type of command back to your servo drive on some technologies. So there's different variants of that, but the whole general purpose of it is it's sending data back of how many rotations has this motor moved. The reason why there needs to be math done to that, and you can't just tell it, hey, this is what motor that we're using, is because the software and the servo never know what size cog you have on the end of your motor shaft. So you could have a cog that's 5 foot in diameter. You could have one that's 5 inches in diameter. It literally has zero clue of that. And when you're in this calibration mode, you're giving your servo the data that is needed to perform the calculation. So what that calculation simply looks like is I traveled X amount of distance and it was X amount of pulse codes. And that then builds a relationship to it's X amount of pulse codes per inch. So essentially that conversion is just made like a distance type of conversion in the same way that we say it traveled 60 miles per hour. And so now that servo system knows it moved 1,000 pulse codes per inch. One thing that it also has to have, it has to have a constant when doing it this method. That constant is, I know from limit switch to limit switch, it's 10 feet. So it's taking that 10 feet as a constant, it's taking how many pulse code counts, and it's basically just doing a divide function. Now it's built that relationship of how many pulse codes it takes to get to an inch, or depending on whatever measurement you're wanting to use. It could be millimeters, and you can change whatever unit of measure you want to measure in. Majority of the time, most Cartesian stuff is done in millimeters. There's sometimes you'll see people do it in inches and whatnot in a standard system, but I've very rarely ever ran across that. And then another thing that's gonna occur with that is the servo, whenever it's running, and it hits one of these limit switches, majority of the time you're going to say one of those limit switches is your 0 point. So what that does is, if we break out our right hand tool real quick, is it creates a 0 point in your Cartesian world. So now everything going that direction is X positive, and everything going that direction is X negative. Now, if you're using one of those limit switches as your 0 point, and also if we're only traveling one direction, you have no X and you have no Y, so you're just traveling in an X. And technically, you don't actually have an X negative because your 0 point's here. You can't travel any further that way, so you can't really travel in negative X. So like, let's say, for instance, at the end of it, we'll just say X positive 10 is all the way at the end at the other limit switch. X positive 9 is at 9 feet from this first limit switch. X8 will be 8 feet from this limit switch. So now you have the ability to command your servo to go a certain point based on that 0 point. Now let's say, for instance, you like to work with X positives and X negatives. What you can do is, now this will be something that's different on every system depending on if you're working with servos or robots. It'll be a little bit different, but majority of the time you can adjust your 0 position, and that may be something that if it's like a FANUC robot, it'll be a frame, or it might be something in an instruction block, or you just might have to do some math where you add a certain amount to this 0 point. So you could do what like an initial offset and say take this 0 number and I want to add 5 to it, right? And so now this is your new 0 position, and so everything's going to be taught off of this new 0 position. So now you have -5 in that direction, and you have +5 in that direction. And a lot of times you'll do something like that if you want things in your system to line up. Like a lot of times with robot, you use different user frames because maybe you have weird work pieces and now your angles are like this. Maybe you're placing on an object that has like a 45-degree angle. And since you're placing on something that has a 45-degree angle, if your Z is this direction and your X is that direction, you really have nothing good to just like go directly in. So it's like, how do I go directly in? Well, majority of the time, if we're doing it, we'll make that our Z, because we look at it as that's our downward motion. So we'll do a Z positive away and Z negative towards, and then our X positive and our X negative will be in this direction. So some of these are are tools to help the programmer be able to manipulate the robot and jog around things, and other of these are just physically building the relationship. So when it comes to like the user frame type of stuff, that's going to be more so just to help the user, whereas whenever it comes to like creating that relationship between the physical world and the virtual world, that is a have-to thing. Your system cannot operate properly without that information. Let's go back to our example where we have our servo with our limit switches. Okay, let's say for instance, we didn't have our limit switches in here. Maybe we only have one limit switch, okay? And we don't have a known constant number. One of the other ways to build the relationship between the real world and the virtual world is to do what's called scaling. And so when it comes to scaling and creating that relationship, you actually do not need the limit switch at all. You don't need a limit switch at all. But what you do need is the measurements of each cog in the system. So you have to do like some mechanical engineering type of math and essentially find out what the diameters of each one of your cogs are, how many cogs you have in the system, do you have pulleys, and there's quite a bit of math that goes into that part of it. And majority of the time, if I have to deal with something like that, I'm going to have a mechanical engineer spit the numbers out for me and give me the gear ratios. That's essentially what you're looking for, is the gear ratios of the system. So after you get a gear ratio and you know you have like a 50-to-1, you can now convert that pulse code count in what's called scaling to get you a known distance. So going back to the encoder, that way whenever we travel, 1 foot, it knows that we've traveled 1 foot because we've traveled 1,000 pulse counts. Now, that may be different. This is where you're building the relationship. Maybe you have a bigger cog on this other system, and so now your system's going to travel further for less pulse counts. So now maybe it's only 500 pulse counts to travel that same 1 foot versus 1,000 pulse counts to travel that same 1 foot. That's kind of like the best engineering way to go about doing the scaling, is to get that gear ratio from a mechanical engineer. Other way of going about doing it, and it's kind of like a cheat method, is to literally just take a measurement. So what you would do is you would say for instance, we'll go back to that 10 foot. You would start out at the very beginning of 10 feet, get your pulse count numbers, travel the 10 feet, get your pulse count numbers again, which is essentially all your virtual world data, and then you will convert those pulse counts the same way it did whenever it did the limit switches, but you're just having to manually do it. Now the constant is you punching in the constant and putting that into your scaling. Now that's you punching in the constant to come up with the ratio of pulse counts to physical space. Now I want to go ahead and dive into vision systems a little bit because they're slightly different in the way that they build their relationship to the world. So when it comes to vision systems, at least for vision location, you're going to use what's called a calibration grid to calibrate the camera and build its relationship to the real world. And the way a calibration grid works is essentially they are a dot grid. So essentially all a dot grid is a grid with dots on it. And those dots are set to a particular increment apart from one another. So you may have a dot grid that is 10 millimeters between dots, or 20 millimeters between dots, 30 millimeters between dots, and then you're going to have the hundreds of dots. And generally somewhere in the corner of that panel or something like that, it's going to tell you how far apart the dots are spaced. And essentially what you do in a 2D vision application where you're locating something on a flat plane is you're going to set that grid as close to that workpiece as possible, so that way your dot grid is calibrated on the same plane that your workpiece is. Now, it doesn't necessarily have to be right on it. It could technically be some inches above it and could be even quite a bit off. But what's going to happen is whenever you train in all those parts, you have to make sure you recalibrate the vision next time. It needs to be recalibrated in the exact same place. Because if you calibrate it up here and then you calibrate it down there, it's going to probably not even locate your parts, because what's going to happen is you're, say for instance, so your camera's seeing something like this, and then if you recalibrate it, what's going to happen is the location in which it's searching, what the dimensions of what it's trying to find is going to change. So like, let's say for instance it's searching for a dimension this size, that dimension is going to do this basically. Now notice like how much bigger that is versus being back here to the camera, because like you got to think, the camera knows nothing about the physical world. All it knows is how big is it to what I can see. So it's basically pulling a measurement from top of the screen here to here from the bottom of screen here to here using pixels. When you get closer, what happens is you're taking up less space here and you're taking up less space here, and it's pulling that measurement with the pixels, and that's how it's coming up with its measurements. So whenever you teach that plane, you want to try to teach it, one, it needs to be taught at the exact same place every time. Two, you do want to teach it as close to your workpiece as possible, because that's going to give you what is like your truest inch. And if you're going to do measurements of the part that your workpiece is, then it absolutely matters. If you're just doing location to do like a pick and place location, it doesn't matter as much, because you're mainly looking for the center of the part, and then you're looking for where it's located at in X, and where it's located at in Y, and where it's located at rotationally. But whenever it comes to measurements, it is quite a bit more important, because your measurement, like I said, is looking off those pixels. If you're telling it this is 20 millimeters, and then you're coming back here and then saying and then expecting it to measure the same 20 millimeters, it'll never measure that same 20 millimeters. So whenever it comes to doing measurement type of applications, then it does matter very much so on the Z height at which you calibrate at. And a lot of these vision systems are starting to have some auto-calibrate functions where you're able to take a grid, put it at one distance, put it at another distance, put it at another distance, and it does its auto-calibration. It does a bunch of math calculations in the background to come up with what its measurements are. And then you may put in an item like this, right? And you could, let's say for instance, you calibrate it way up here, and then you want to pull a measurement on something like this. What you can do is you could take your CAD data, and you could say, hey, this is, for sure, this is 20 millimeters, right? And so now what happens is the same thing as like a frame in a robot. Now, even though you taught your vision, let's say for instance at 20 millimeters up here, this is what 20 millimeters looks like. You're saying actually, let's go with this part being 20 millimeters as well, this is 20 millimeters. Now you've created essentially a frame on top of that main calibration that builds a different relationship to this particular part. So that way, whenever you're going through and you're training in different parts, and this is where this will become very important, is whenever you have something like this, notice you're going to have a pretty major Z height difference there, right? If you have two parts, you're trying to take measurements on both these parts coming in, this part right here is going to measure differently in comparison to this one because the Z height's so different. On a process control standpoint, it's going to be super complicated to try to have every part come in on the exact same Z height. It's almost impossible. So what you do is you just say, hey, this is my new 20. Let's say, for instance, these are both 20 millimeters around exactly. They're not, but let's just say they are. So what you would do is, whenever you teach this part, is you're going to say this is 20 millimeters. Whenever you teach this part, you're going to say this is 20 millimeters. And then it'll be able to pull the measurements accurately every time. Now, what can happen as an issue is if this ever changes in Z height. So for some reason, if there's ever a modification to this part, and this part grows in Z, now the file that you taught in to be able to pull data, measurement data from this part is not going to be right. So guys, I think I rambled on enough for this particular video. If you'd like for me to break down any particular aspect of this video, let me know. If you have anything you'd like to add, things that I missed out, like I said, this is a ton of content to try to cover underneath one video. This video already turned out being way longer than anticipated. I kind of wanted to just make this a brief video on Cartesian systems and like real world versus the virtual world, and kind of dive way more into like the technologies of how these actual systems are set up and how they work in the background a little bit more. This particular 30-minute session is probably just as valuable as any college session that you would have. If you're a manufacturer and you'd like for us to implement any robotic systems, vision systems, or anything along those lines, feel free to reach out. We specialize in robotic cells, generally with vision, line tracking, other technologies like that, Cartesian robots. Also diving deep into the mirror technologies, mobile autonomous robots, really taking our company in that direction as a secondary core competency. But our contact information will be here at the end of this video. Thank you guys for viewing, and I'll catch y'all in the next one.